Okay, so let's get started. Last time we were discussing the notion of weak entity sets, right? So these are entity sets that require other entity sets to in some sense support them. Okay, so these entity sets are weak because some of their attributes come from other classes that they have relationships with, right? So we saw the example of courses, where a course requires a university in order to support it. So you have the course number and the university name as the keys for the entities within this weak entity set course. And you have this relationship, which is a supporting relationship, which goes from course to university. This is an exactly one relationship, so it's not an at most one because it's a semicircle. Okay, so that's a necessity for a weak entity set, that there is no dangling pointers, that it's a semicircle. Okay, so we saw these two examples. University is a supporting entity set for team. Affiliation is a supporting relationship. So the supporting entity set, and the supporting relationship. Similarly, this is a supporting entity set, this is a supporting relationship. And we saw this example of where weak entity sets naturally arise. This is where I'm converting a multi-way relationship into a collection of two-way relationships. So here, purchase ends up being a weak entity set. It has a bunch of supporting entity sets: product, store, and person, and there are supporting relationships, right? So there's a product of relationship, store of, and buyer of. And so if you look at a purchase entity, it borrows its attributes from each of these supporting entity sets. So it borrows name and category, address and name, and SSN. These form the key for the purchase entities. Okay? Is this clear? Any questions about this? So this is what we covered last time. Okay. So the last topic within the ER spectrum is design principles. How do you design a good ER diagram? What constitutes a good ER diagram? Okay, and so like I mentioned to some of you last class, designing an ER diagram is a little bit like an art. It's like, for instance, how you would design classes in an object-oriented programming paradigm, or how you would design, let's say, a floor plan if you were an architect. Okay, so it's a little bit of an art, but there are some key guidelines or key design principles that we can draw on in order to make better decisions, make better designs. Okay, so the design principles are the following. So these three are the ones that I'll be covering in class: be faithful to reality, avoid redundancy, and pick the right kind of element. These are perhaps the most important. There are also other ones like simplicity and choosing the right relationships. For this, I'll let you look at the textbook for examples. Okay, so let's start by talking about being faithful to reality. So let's take the example or the case of where the arrows should be and where they shouldn't be. Okay, so I'm just focusing on the arrows from a relationship. Okay, so here you find that there's an arrow going into product, and this is a purchase relationship. This is not faithful to reality because a person may purchase multiple products, right? If a person is allowed to purchase multiple products, this arrow is not correct, and therefore we don't want to use it. Okay. Okay, similarly, if you have a precedent relationship between a country and a person, then a country can have at most one president. So you want an arrow going in you want an arrow going into this entity set, right? So there's a need for having an arrow because it's not clear given that there exists this constraint. You want to represent that within the ER diagram. Okay, so in this case, you have an instructor-course relationship, and this is the relationship teaches. If an instructor can teach many courses at once, and each course can be taught by many instructors, then this is fine. But if each course can be taught by precisely one instructor or at most one instructor, then you want an edge going in here. If each instructor teaches exactly one or at most one course, you want an arrow or a semicircle going in here. Okay? Does that make sense? So if I have a, let's take these cases, right? If I have a semicircle going here, when would I want to have a semicircle going here? Yep.
When every instructor, or you mean going to course or instructor?
Going into course.
When every instructor has to teach a course.
Exactly. So if every instructor has to teach a course every semester, then maybe you want to have a semicircle going into course. Similarly, if you have, let's say, an arrow going in here, what does that mean? To going into instructor. Yep. Yeah, so each course has 0 or 1 instructors. But if we know for a fact that each course has to have at least one instructor, right, has to have precisely one instructor, then the arrow is not sufficient. We want to have a semicircle. Okay? So we have to be faithful between either having an edge without a direction, an edge with an arrow, or an edge with a semicircle. Okay? We need to be precise about which of these three meanings we prefer and model reality faithfully. Any questions about this? Okay, so that's our first design principle. We need to make sure that we are modeling reality faithfully. The second is about minimizing redundancy. Okay, so this is a particularly important problem because this has performance implications in the database. So redundancy occurs when we are saying the same thing in two different ways. We are using two different ways to represent the same information. Redundancy certainly wastes space. So this is one issue with redundancy. And more importantly, this encourages inconsistency and leads to poor performance. Okay, so the inconsistency basically leads from the fact that if you have two ways of recording the same fact, these two ways may become inconsistent with each other, and because of that, it may lead to errors in your data, right? So if you change one and you forget to change the other, it leads to inconsistencies. You don't want that happening. Okay, so let's take this example here. I have a beers entity set and a manufacturer's entity set in a relationship, manufactured by. The key for beers is name, the key for manufacturers is name. Okay, so you can identify a beer using a name, you can identify a manufacturer using a name as well. Okay, so from the perspective of redundancy, this design is good because it lists the address of each manufacturer exactly once. Okay, it is the address of a manufacturer is associated with a specific manufacturer, and you're listing it precisely once. Let's consider a case where this is not that great, right? So if in addition to having an address associated, or actually forget the address, if for the beers you added an extra attribute corresponding to the manufacturer and you had a separate relationship relating the beers to the manufacturers, then you're representing the same relationship, same information in two ways, right? One via a relationship and the second via an attribute. Does that make sense? So you don't want that to happen. So you don't want to have an attribute when a relationship conveys the same thing. Okay, so you need to pick between attributes and relationships carefully, but you definitely don't want to have both. Okay, so the reason why you don't want to have both is because there are update issues. So if I went and changed, for instance, the name of the manufacturer, so I don't know, Coors Light or Coors decides to change its name, or Anheuser-Busch decides to change its name to some other company, then I want to go and I will need to update the name in the manufacturer's entity set, but I will also have to go and update the attribute for all the beers that are manufactured by that manufacturer. Okay, so I will have to make this update twice, which is annoying, right? And this could lead to inconsistencies. If I change one and don't change the other, this could lead to problems. Okay, so update issues are one problem. The other problem is that it's wasteful. You're recording the same information twice. Okay, so this is yes?
Shouldn't there be a semicircle there? I mean, every beer has to be produced by some manufacturer.
Sure. If every beer was manufactured by exactly one manufacturer, as opposed to at most one manufacturer, then you might want a semicircle here. So this is not as precise as it should be. Yep.
But that would imply that the beer is only made by one manufacturer, but it's not really realistic. So would that make it inconsistent?
Sorry, what do you mean by each beer is made by exactly one manufacturer?
I mean, you could have multiple manufacturers making the same beer, right?
So, okay, so at least in this particular entity relationship diagram, a beer is uniquely identified by its name. There are no two manufacturers making the same beer. Okay? If there are multiple manufacturers making the same beer, I wouldn't want an arrow or a semicircle going into this. Any other questions? Okay, so this is the first and simpler issue. Now we get to the slightly hairier issue, which is sort of removing the entity set entirely, the manufacturer's entity set entirely, and having it as all as attributes of the beer entity set, right? So you've moved the name of the manufacturer and you've moved the manufacturer address both as attributes of your beer entity set. So the reason why this is bad, so the first thing is that yes, you're recording the information about which beer is manufactured by which manufacturer once, so that's good. But this is still bad because you're repeating the manufacturer address multiple times for every beer that's made by that manufacturer, right? And we know that a manufacturer is located at one place, so you don't want to repeatedly sort of store the same information. This once again leads to update issues. So if you went ahead and updated one tuple corresponding to the address for one manufacturer, you need to go and update all the other, I use the word tuple, I should have said entity. If you wanted to update one entity, you need to go ahead and update all the other entities, okay, corresponding to the same manufacturer. Does it make sense? Okay, so this design is wasteful because it's repeating the same information multiple times for multiple entities, all of which contain are corresponding to the same manufacturer, right? So you don't want to repeat this information multiple times. It would be much better to take this information and store it as a separate entity set. The other reason why this is bad, so the first reason is that you're repeating the manufacturer address multiple times. This is wasteful and could lead to update anomalies. You updated once but not updated the other. The second reason why this is bad is if for some reason a manufacturer temporarily stops making beer, then you lose the manufacturer's address as well, right? Because there's no, because there are no beers associated with that manufacturer, there are no entities corresponding to any beer within this entity set, and therefore you lose the information corresponding to the manufacturer address when this happens, right? So this is another problem that arises because you are relying on the fact that there exists these entities within the beer to store additional information, if you will. Okay, so let's get to a rule of thumb for this. Okay, so when do we pick between entity sets and attributes? So the rule of thumb goes as follows. An entity set should satisfy at least one of the following conditions. The first is that it is more than just a name, so it has more than just one particular attribute. It has at least one non-key attribute. So it doesn't just have key attributes, it has at least one non-key attribute. So it's more than just some item, it's got attributes as well. Okay, so that's one condition. The other condition is it is the many in a many-to-one or many-to-many relationship. This is another sufficient reason for us to designate something as an entity set as opposed to being an attribute. Okay, so can you guys explain to me why each of these rules might make sense? Yes?
If it's just a name, then it can just be an attribute.
Yep. So if it's just a name, it can just be an attribute. More importantly, if it has any other non-key attributes associated with it, if you convert that into an attribute, you're going to repeatedly store the non-key attributes, right? So, for example, in the manufacturer address case, we ended up storing the manufacturer address multiple times, even though that information was not necessary for codifying the relationship between beers and manufacturers, right? So you were storing wastefully. So that's one issue. So that explains the first part of this. How do we explain the second part? If it is a many in a many-to-one relationship, why would we want an entity set as opposed to an attribute? Yep? Exactly, right? So the reason is that you can't have multiple values within one attribute. An attribute is has a unit, right? So you can't really have a set of values corresponding to an attribute. You can't, for instance, say that here are multiple values that you store within an attribute. You can only have one atomic unit within an attribute, right? So you can't store, if a beer is manufactured by many manufacturers, you can't really store that entire set as an attribute. You'll need to create an entity set to explicitly store that relationship. Okay, so let's walk through these two. If it's still not clear, let's walk through how I would apply this rule to this example. So why is this ER diagram good? Why do these entity sets make sense? First, the manufacturers deserves to be an entity set because of this non-key attribute address, right? So there is one key attribute which is name. There's a non-key attribute address. So it deserves to be an entity set, right? So it has at least one non-key attribute. Why does beer deserve to be an entity set? Well, this is because of the other rule, right? So beer deserves to be an entity set because it is the many of a many-to-one relationship manufactured by, right? So here you see no arrows. So if you wanted to get rid of this guy and add an attribute beer, this would not work because you would need to store a set of beers, right? B1, B2, whatever, right? And you can't do that, right? You can't store multiple values within an attribute. An attribute has to be atomic. And because of that, you can't change beer into an attribute of manufacturer. Yes? So at least from the ER diagram standpoint, the attributes are atomic. Any other questions? Okay. So let's say we didn't have information about the manufacturer address. If we didn't have the information about the manufacturer address, it would be totally fine to store manufacturer as an attribute of beers. Okay, it would be completely okay to store manufacturer as an attribute of beers because manufacturer was the one in a many-to-one relationship with beers. So this information can be stored along with the beer information. Okay, so this is bad. So the same example, but with an entity set instead of an attribute. This is bad because manufacturer is nothing but a name. It's just consists of the key attribute name. And it's not at the many end of a many-to-one relationship or many-to-many relationship. And because of that, you should not have it as a separate entity set. You should just have it as an attribute of beers. Okay, so that's a couple of simple examples about how to pick between entity sets and attributes. Hopefully that gives you some sense as to how to do this. There's a lot more examples in the textbook, so please go take a look at that. I won't have the time to cover that in class. So here's a review of the ER stuff. We talked about the notions of entities, attributes, and entity sets, the notion of relationships, multi-way and two-way relationships. We talked about the roles and attributes on relationships. We talked about subclasses, so this was the basic stuff. And then we talked about the notion of keys and referential integrity constraints, these arrows and what they mean. And we also talked about the weak entity set notion and some design principles, right? So this is all that we're going to cover for the ER diagram stuff. So there are some assigned readings for this, so please go take a look at that because they give you more examples, more intuition as to why some of these designs make sense, or some of these explanations, rules of thumb make sense. Any questions before I go to the next topic? So often it actually, even if you have some unanswered questions, when we get to the next topic and we talk about how to translate this ER diagram into something that the database understands, a lot of these questions will get answered. So just even if you have some lingering questions, ask me now. But if some aspects are still fuzzy and they don't fully make sense, we'll come back to that later. Yes? Okay, what if you have an entity set with many attributes and all of them form a key? Okay, so the question is, you have, let's say, entity set E1, you have attribute A, attribute B, and A and B forms a key, and you're considering, and you have a relationship with entity set E2, okay, and let's say this is, to make it more interesting, maybe we can make this a many-to-one relationship going into E1, and E2 has maybe two attributes, let's say C is a key, and D is not the key, okay? So let's look at this diagram and try to answer your question. First, should E2 be an attribute or an entity set? Well, it needs to be an entity set for two reasons. The first is it has one non-key attribute, and it's the many in a many-to-one relationship, right? So E2 is good. We don't need to worry about E2. The question remains, should we have E1 as an entity set, or should we have it as attributes of E2, right? So the alternatives are I either use this guy, or I have E2 C D A and B. Actually, these wouldn't be underlined. Okay? So let's talk about whether this is better than this. Okay, so at least according to the rules, this is actually better than this because this representation does not, so E1 does not have any non-key attributes, and it is the one in a many-to-one relationship. So it does not have any other many-to-something relationships where it's the many, right? Because of that, E1 should not, technically not be an entity set by itself. It should be an attribute of E2. Does that make sense? Okay. So, yes?
Yeah, maybe it's from the previous class, but how to determine if an attribute or a pair of attributes are key or not?
So the question is, how do you determine whether an attribute or a pair of attributes are a key or not? This is again coming from the application. So if the application says, you know what, people are identified by SSNs, then you would say SSN is a key. Okay, if students at UIUC are identified by their UINs, that's a key, right? So this is coming from the application. So this is not, there are no rules of thumb as to how to pick these keys. These come from application requirements. So this is just like how the real world is telling you you should model these things.
And in this class, when letter is underlined, it's a key, right?
When any attribute is underlined, it's a key, right? So together, A and B form the key for E1. Yes?
So I'm still confused why UI is not
Okay, so why is E1 not a good entity set? Okay, so another way to think about this relationship, okay, is that this relationship is, again, we will get into why this makes sense in the next class when we translate this. But this relationship is basically saying that, look, some A1 B1 pair is associated with some, or AI BI pair is associated with some CJ. Okay, basically the keys here A and B are associated with some. Sorry, I should not be pointing without showing you guys what I'm pointing at. So the A and B, which is the attributes of E1, are associated with some of the attributes of E2, right? So this is what the relationship is encoding, right? So one way to think about how this information is being stored is you have one bit of, okay, let me try to erase some of this just so that I have some space. Is there a way to reduce the size of the eraser? Let's see. No, I don't think so. Okay. They have this giant eraser that erases most things. Okay. Okay. I think I'm done. All right, so let me get rid of this guy. I don't need this guy. Okay, so what does this? So if I were to, again, this will become clear in the next half, but how do I store this information within a database? Okay, I'll give you the high-level view, and then I will try to make an argument for why it's better off storing these guys as attributes. A high-level view of how I would be storing this information is I would store something corresponding to this entity set E1. I would store something corresponding to the relationship, and I would store something corresponding to the entity set E2. Okay? So for storing the information corresponding to E1, I would be essentially storing A-B pairs. So A1, B1, A2, B2, and so on. Okay? That's the kind of information that I would be storing for entity set E1. For entity set E2, I would be storing C1, D1, C2, D2, and so on. Okay? And for the relationship, I would be storing, for example, the smallest possible representation would be A1, AI, BI, CJ, AI1, BI1, CJ1, AI2, BI2, CJ2, basically indicating which of these entities in E1 are related to which entities in E2. Make sense? Okay. So now, notice that since this is a many-to-one relationship, each CI is associated with exactly one, or at most one, guy within E1. Okay? So I could take this information and then append it to this information, right? So I could say, yeah, instead of having the C1, D1, I could say this is C1, D1, and then A whatever, AX, B, AX1, B, X2, C2, D2, AX2, A, okay, let me call this Y1, AX2, B, Y2, and so on, right? Or maybe these two are the same. I'm being terrible with my subscripts, but let's call this BX1 and BX2, okay? So I can take this information and append it to each of these rows, correct? Now that I have that, do I really need this anymore? Because I know which AIBIs exist. They are part of this table already, right? They are already part of this information that I've recorded. So I don't really need this information anymore because this information is not storing anything new. It's whatever is necessary is already here. At a high level, does that make sense? Again, when we translate it, I promise you it will get clearer, and you should ask me the same question then. But at a very high level, I hope you get the idea that there's some information that you're storing corresponding to entity sets, some information that you're storing corresponding to relationships, and therefore we need to reason about whether this information can be combined and stored more compactly. And in this case, my argument is that yes, you can by converting it into an attribute. Okay? Yes?
Why the A and B are not the key when they become the attribute of the E2?
So for E2, C is sufficient as a key, right? So if C is a key, it will stay the key even if you add these other guys as the attribute, right? Think of it in the following way. What would be a good example here? So let's say, let's assume that you had, okay, so let's say E2 was beers, right? You have the name of the beer and the type of the beer, so the name is a key. E1 was manufacturers with manufacturer name and manufacturer ID. And let's say that the manufacturer name and ID together form the key for manufacturer. Now, if I move name and ID as attributes of beer, the beer name is still the key for beer, right? Because it uniquely identifies everything else. So I don't need to add, in this case, A and B as attributes of the key. It's not necessary. C will be sufficient to form the key. Yes?
I remember that my second reason, that is in the multi-wire relationship.
Yeah.
Because E1 is not that many, so you can, what do you mean by E1 is not that many?
No. E1 is not the many in a many-to-one relationship. So the only relationship that E1 is participating in is this relationship. Here it is the one component. It's not the many component. So if there was no arrow here, it would be a many. Okay? All right. I'll go ahead and we can return to this later if it's still not clear. Okay? All right. So we are done with the ER stuff. And let's talk about the relational model. Okay? So the next step is basically, we talked about how to design this ER diagram, which is a doodle about your data. The next step is to translate this conceptual design, this ER diagram, into a database management system format. Then once you have that, you have your database that's set up, right? So we saw this sort of steps to get to building your database application earlier. So our focus right now is going to be step 2, which is translating this conceptual design into a database format. But before we get there, we need to talk about what the database format looks like. So the database format is what is called as a relational model. It's a different way of modeling your data than the ER model that we talked about earlier. So the relational model basically gives rise to a schema. Like I described in the first class, a schema is a structure, a framework for describing your data. The ER model basically gave rise to ER diagrams as a means of specifying the relationships and entities in your data. The relational model, which is the next step, which is what the database understands, uses the notion of tables. Okay, it uses the notion of tables with column names as the attributes and rows as the tuples. Okay, so these are called as tuples because they are values that are appended to each other. Okay, and the last step after you have specified how the database understands this is how it's actually stored. And that's not something we are going to be covering today, but there's a gap between what is declared to the database and what is actually stored within the database. And often databases use complex file system organizations, complex layouts, and indexing structures that will allow us to get to the data efficiently. Okay, so this is not our topic for today. Our topic for today is the middle step, which is the relational model. Okay, so some contrasting observations about the ER model versus the relational model. So both of these are used to model data. The ER model is very well suited for capturing application requirements. It's easy to understand. So you have these concepts like entities, relationships, and attributes. It's more intuitive, easy to grasp. But on the other hand, this is not very well suited for computer implementation. Okay, so does not have a direct one-to-one correspondence with what would be actually stored in the database. Okay, and it does not have any operations on its structures. The relational model, which is the next level below, has just one single concept. It is the notion of a table, which is also called a relation. Okay, so be warned, the term relation is used in many different places in many different contexts. So just beware of that. So the term, when I mean relation here in the relational model, it essentially refers to a tabular view of the data. It's a table. Okay. So the relational model, in the relational model, the world is represented with just a collection of tables, nothing more. Okay, so there are no differing types of things. There's no entity set and relationship and so on. It's just a collection of tables. That's it. Right? So because of its simplicity, this is fairly well suited for efficient manipulation on computers. So this is the outline for the rest of today. I'll be telling you about what the relational format is. We'll be talking about how you use the database query language to define or declare this relational format. And then we'll start talking about the translation from the ER diagram to the relational format. We'll talk about the simple cases today, the more advanced cases tomorrow or Monday. Okay, so the very basics, here is an example of a relation or a table. The way a relation looks like is you have a relation name. So here this relation name is products. You have a bunch of attributes, name, price, category, and manufacturer, and a bunch of rows or tuples. Okay, so going through these step by step, product is either the table or the relation name. The name, price, category, and manufacturer are either called the attributes or the column names. Okay, these guys, Gizmo, Power Gizmo, Single Touch, and Multi-Touch are what you call the tuples or the rows or the records, right? So all of these are equivalent. So once again, a relation basically consists of this structure above, so the relation name and the attributes, as well as stuff that's stored that agrees to that structure, right? So you have the tuples, also known as the rows, also known as the records. Okay, so like I said, each relation is defined by a set of attributes. Each attribute has a type. This type is also known as the domain of an attribute. This type needs to be an atomic type. So returning to your question about why not use an array, arrays are not very efficient to use within a database system. So that's another reason why we force these attributes to be atomic. So attributes are atomic. Examples of attributes include integer, string, and real. So a relation is defined by a set of attributes, but it contains a set of tuples or records. Okay, so these records basically have values assigned for every attribute within the relation. Right? So like we saw here, this Gizmo tuple basically has a value corresponding to the name, a value corresponding to the price, category, and manufacturer. Okay, so even though the relation was represented in this way, there are many alternate representations of the same relation that are all equivalent. Okay, so let's look at that. So first, a relation is a set of tuples, not a list of tuples. So reordering the rows or reordering the tuples in a table does not change the relation. It is the same relation. It's the same table. Similarly, a relation is defined by a set of columns, not a list of columns. So if you reorder the columns, it doesn't change the meaning. It doesn't change the relation. It doesn't change the table. So here are some alternative representations for the same table. You had this one table here. If I shuffle some rows or records, I get the same table. If I shuffle the attributes or the columns, I get the same table. It doesn't change. Okay, so all of these are equivalent representations because essentially a relation consists of a set of attributes and a set of tuples. So even if you reorder these guys or reorder these guys, it's still the same relation. Okay? Any questions so far? Okay. So let's talk about the distinction between the schema and an instance. So we talked about the notion of a relation and the notion of tuples. So basically this will help us clarify that. So the schema in some sense refers to the structure or the format or the scaffolding of a relation, and a schema of a relation is basically just the relation name plus the attribute names of the relation. So for example, in the previous case that we saw, the product table or the product relation plus the attributes name, price, category, and manufacturer form the schema of that relation. They form the structure of that relation. This is enough to tell me how the relation is going to look like. Right? So in practice, however, one additional aspect is that when I'm defining a relation, I often add the domain for each attribute. So I might say that, hey, this is a string, this is an int, or whatever. But that's another way of specifying the schema, but in practice at least. But those are equivalent. So the way I would think about a schema of a relation is the relation name plus the attributes. When defining a schema of a relation, I might also mention what the attribute types are. Yes?
So, like, if we add in, what the attribute types are, would it be like string name and then comma in price?
Yeah, I'll talk about how that will look like in the query language in a bit. Okay? So this is a schema of a relation. A schema of a database is a collection of relational schemas, right? So you basically have a bunch of different relations. You could have one corresponding to the product, one corresponding to the vendor, and so on. Okay, so these are a bunch of different relation schemas. So each of these is a separate table. Okay? So we talked about the schema. What's an instance of a relation? So that's the other concept. So the schema was basically the scaffolding, the structure, which is the relation name and the set of attributes. The instance is an instance of that relation. It's a concretization of that relation. It's a exact value for that relation. So here you see that this relation contains a set of 4 tuples or 4 records or 4 rows. Okay, so this entire thing is a concrete instance of that relation. Okay, it is an instantiation of that relation. So to go back to the relational schema versus the database schema concept, so you have a relational schema is basically a relation name and a set of attributes, and the instance of a relation schema is a set of tuples with each tuple having a value for each of the attributes. A database schema is a set of relation schemas, and and the database instance is a set of relation instances for each of the tables, for each of the relations, right? So basically you have your database schema has declared that, hey, there are n relations that exist in the database. Your database instance would be basically an instantiation of this, an instantiation of this, all the way up until an instantiation of this. Okay, so it's n relation instances of type R1, R2, all the way up until Rn. Any questions about this? Okay. So next, the notion of updates, right? So so the way you need to think about how you would update the data. So updates happen to the data fairly frequently. So the instance actually gets updated fairly frequently. The way the data instance would keep getting updated would be, for example, to add a row or a tuple, delete a row or a tuple, or modify an attribute of a tuple. Okay, so these sorts of updates happen very frequently, right? So the updates to the database instance, updates to the relation instance happen very frequently as the data changes in the real world, right? So the database maintains a current database state, which is a current schema and a current instance for that schema, and that instance constantly keeps getting modified. So updates to the data happen very frequently. On the other hand, updates to the schema, updates to the structure of the data happens much more infrequently. Okay? So what are the ways you can change the structure of a relation, change the schema of a relation? Well, you might add a new column or an attribute, you might drop a column or an attribute, you might drop an entire relation. All of these are do happen, but they happen much frequently compared to changes in the data, changes in the instance. Okay? The reason why they happen why the changes to the schema happen more infrequently is because they are way more expensive, and often your application requirements don't change that frequently for you to say, oh, you know what, maybe I don't need to store the student email address anymore, so I'll go ahead and delete that for all students, right? So your application requirements typically happen at the start, so you would stick to your relation schema, but the relation instance keeps getting changed, right? So you may have students coming and going, you might add and delete tuples, but you will keep the structure of the data the same. Is that clear? Okay. So we talked about the relational format. We are done with this. Let's talk about using SQL, which is the standard relational query language. It's also called as the structured query language. Okay. And within SQL, there is a component which is called the data definition language and a component which is called the data manipulation language. So we'll be talking about the data definition language because we are interested in setting up the database. Okay, so the simplest form for setting up a relation within your database management system is to use the create table command. So you would basically say create table name, and then you would list the attributes and the domains of each attribute. Once you are done with the relation, and this is a very, very expensive and very infrequent operation, you may say drop table name, and this would basically remove that table or remove that relation from your database. So we talked about domains, right? So attributes and domains. So what sort of domains can attributes take, or types? So the common types are int or integer, real or float, also a fixed length string of characters. There's this varchar, which is something that I've only seen in the database management system context. It's a variable length string of up to n characters, and you have date and time. These are also types or domains that you can use. Okay, so these are the types that you can use. Let's talk about a concrete example. So if I wanted to have a sales table which has the attributes bar, beer, and price, maybe I might use this kind of a create table statement where I say create table cells, parentheses, bar, with maybe the type being car20. So this says that it's going to be a fixed length string of 20 characters. The beer is a varchar 20, which means it's a variable length string of up to 20 characters. So it can be smaller, it can be larger. And real for the price indicates that price is a real. Okay. So next I'm going to be talking about the notion of keys, key designations when you're creating a table or creating a relation. Before that, let me talk about the notion of null values. Okay. So there's a special token or special identifier for when a value is undefined, and that identifier is this value called null, N-U-L-L. It's typically written in caps. So this is a special value for for databases, special value in the database parlance. This is handy when, for instance, you add a new column because you don't know the value of that column yet. So if you've gone and added a new column, initially that column will be populated, unless you specify otherwise, initially that column will be populated with null values. Okay, so let's say you have you had only one attribute in your relation, which was A, and this was A1, A2, blah, blah, blah. And then when you went ahead and added a new attribute B, okay, so if you went ahead and added a new attribute B, at the start, the values corresponding to B will all be null, unless you specify otherwise, but typically it will be null. Okay, so why is null useful? Null is useful for two reasons. The first is a value is not known, okay, or a value does not exist. Okay, so an example of when a value is not known is maybe a student's birth date, right? So this is a value that's not known, but we know that it exists. When a null value could also be used when a value does not exist, right? So home address, maybe I don't know, a student is homeless. You don't want that to, so you might use a null value to indicate that a student is homeless or between two homes, right? Okay, so back to the notion of keys that I promised that I would cover. So keys in a relational model are similar to keys in an ER model. So like in the ER model or the ER diagram, a key is used to uniquely distinguish an entity. Here it's used to uniquely distinguish a tuple or a row or a record. Okay, so a set of attributes forms a key for a relation if no two tuples in that relation instance, in any relation instance, can have the same values for all of those attributes. Okay, so designating something as a key means that for all relation instances, no two tuples will have the same values for those attributes. Okay, for the exact same values for that set of attributes. Okay, so if you say that, hey, you have a relation R with A, B, and C, and A and B are the key, then you cannot have two tuples at any point such that their values are the same. Okay, so C1, C2. You cannot have this if you have said that A, B together form a key for R. Okay, so at no point can you have two tuples which have the same value for the set of key attributes. To designate a key, you have two ways of doing it. One is to call something a primary key. There can be only one such designated set of attributes, or you can use the keyword unique. Okay, so there are two keywords. You can either use primary key or you can use the keyword unique. Yes?
Here, can you have something like A1B and A2B?
Yeah, that's totally fine. You can have A1B and A2B because it has to be the pair of values, not individual values. This is totally allowed. Okay. So in order to declare keys, I would either use the primary key or the unique distinction. In both of these cases, the implication is that no two tuples will agree on all of the attributes that are listed within this designation, within either primary key or unique. And I'll explain the distinction between primary key and unique in a little bit. So there are two ways of declaring primary key or unique. The first way is to just say, hey, I'm going to say unique or primary key at the end of the attribute declaration. So I might have create table beers, name, type of the name, which is car20, and then I add the keyword unique, or I can add the keyword primary key. Okay, that's totally fine. Now this works if I have a single attribute that is my primary, that I want to designate as a key, or either via primary key or unique. However, if I have a pair of attributes like we saw in this context for A, B, and C, if I have a pair of attributes that I want to jointly say is my key, then this can't work. I can't do it in this way because it's associated with one attribute. The way I would have to do this is to explicitly indicate this at the end of the declaration. So I would use primary key bar comma beer if I want to say that bar and beer together form a key for this relation. Okay? So this form, like I said, is essential if the key consists of more than one attribute. If it is just one attribute, then I can either place it here or I can place it along with the corresponding attribute. If I have more than one attribute as part of the key, I would have to place it at the end of the declaration. Okay, so now for the distinction between primary key and unique, there are variances in implementations of various databases. So you should go and look at what your favorite database system that you're going to be using, for instance, for your project, actually how it implements this. But typically, standard SQL and SQL that's implemented by almost all database systems obeys the following rules. So it basically says that there's at most one primary key for a relation, but there can be several uniques. Okay, so at most one primary key. You can certainly not designate a primary key if you'd like, but there can be at most one primary key for a relation, but there can be several uniques. So if you are using a primary key, then no attribute of a primary key can be null at any time. The reason why is because you can't really compare two null values with each other, right? You don't really know what their actual values are, and therefore you shouldn't be able to compare between them. So you don't, in order to be able to check whether two tuples have the same set of values for the primary key attributes, you need them to not be null, right? You need them to have actual values. So no attribute of a primary key can be null in any tuple. However, uniques don't have that restriction. So the attributes that are declared as unique may have null, and there may be several tuples with null. Okay? And so what that means is if you have several tuples with null, basically what that means is you are not enforcing a key constraint for the values that are null. It's basically assumed that the null values are not equal to each other. Okay, so unique basically says, hey, you know what, I'm okay with using nulls for designating values that I don't know about yet, but if I know the value, then I'm going to make very well sure that those values are unique. Those values don't overlap with other tuples. Make sense? Yeah.
Like when you create the primary key into the space, do you assign the value of null, or do you like assign the real value of the primary key when you create it?
Yeah. So you can create a database schema without inserting any tuples. Primary keys typically you would not be adding as a column after you've added some data. So you can't really add a column that's a primary key because that by default will get filled in with null values. Okay, so you'll be designating typically primary keys at the start of your, when you declare a relation, and as you're adding new rows or new tuples, you would be making sure that every new thing that you add does not overlap with any existing thing. Okay, so that's how you would enforce it. Any other questions? Yeah. Why can there be several uniques in a relation? Okay, so let's consider the case where I have a student table. Okay, so a student, maybe I've decided that I really like, okay, so when a student gets admitted to Illinois, they get assigned a UIN. Okay. After they come in, after a little bit of time, they get assigned an email address. Okay. So I know that both UINs and email addresses are unique. Okay. But I might prefer to use the UIN as my primary key and have the email address as a unique. When the student gets admitted, they might have a precise UIN, so that's not null at any point, but the email address may be null up until the point where the student sets up their email address, at which point I will change it to an actual value. But those values should not overlap. No two students will have the same email address.
For example, if you have 0 uniques in a relation, how do you know?
Sorry, speak up.
If you have 0 uniques in a relation,
Yeah.
how do you know which one is the key?
So if you have several uniques within a relation, they are all keys. Okay. So in the ER diagram context, we only allowed one key because that was a limitation of the ER diagram. You can't really represent multiple keys easily if you're doing the underline notation. So you had only one key that was used in the ER diagram. In a database, in the relational model, you are allowed to have multiple keys, and each of those keys can be designated either using primary key or unique. You can have at most one primary key. So basically you're saying that at most one really important key that I want to ensure that is never null, but other keys can also exist. So it is able to capture more constraints than the ER model. ER model only allowed you to capture one key constraint. Yeah?
So both of them can specify one key. Both the primary key and uniques can specify keys in relation.
So yes, so if I have both primary key and unique separately for the student table, for instance, then what that says is I don't know, the UIN is a primary key, so that's a key. The email address is unique and therefore is also a key. Okay, so both of these are keys and are independent keys. In the ER model, I'd have to pick one. I'd probably go with UIN as the only key that I would designate in my ER diagram. That would be the only thing that I underline in my ER diagram. Any other questions? Okay. All right. So beyond primary key and unique, there are two other declarations that we can make for an attribute. One declaration is not null, so I can say that, hey, this attribute will never take on a value null, but it says nothing about that whether that attribute can be the same value for two different tuples. Okay, so it doesn't have a key kind of restriction, only says that that value has to be not null. The other declaration is a default, so you can say that this value takes on this default value. Okay, so by default, if you don't use the default keyword, then the default will be null. But if you want the default to be something else, then you can specify that using the default keyword. Okay, so for example, if I wanted to create a new table called bar customers, where the name is a primary key, and it also has attributes address and phone number, I can, for instance, set the default address to be some specific address, right, if I want to do that. If I don't have the default keyword, then what that means is the default value is null unless explicitly specified. So the phone attribute will, the default value will be null. Okay? So, so for this specific example, if I insert the fact that Sally is a customer into this table, I would basically have a tuple corresponding to Sally, 123 Sesame Street, and phone equals null. Okay, so if you had declared, for instance, phone as not null, then this update would be prevented, right? So if I declared that this attribute, for instance, if I had this as not null, what that basically means is that I wouldn't be able to insert a tuple where I only specify the name. I would have to specify the phone number as well. Yes?
Should the type for name be var count?
So the why it could be, I mean, so if I wanted to prevent, if I wanted to use a fixed length string independent of the length of the name, then I might want to use a car, but typically varchar is preferred over car because it can be stored more compactly. Yes. Any other questions? Okay. So, so the distinction between varchar and char is very subtle. It's just about how it's stored in the data. It doesn't have, functionally it is the same, right? From a use standpoint, it's the same. It's just that if I know that the values are often smaller or often shorter than the max length, then I might want to use a varchar because the database can store that more efficiently. But functionally, from a user end facing viewpoint, it doesn't really make that much difference. Yeah.
So this example, name, address, and phone, they are all unique, right?
No, I have not specified that they are unique, so why would they be unique? So all that I've specified is the name is a primary key. So that will be unique. I mean, that will be a key.
Okay.
But otherwise, I've not specified anything else, so they won't be, they need not be unique.
So what's the name of the things that are like not unique and not primary key?
There's no, they're just ordinary attributes.
Oh.
Yeah. Okay, all right. So we talked about how you set up your schema, but how do you modify the schema? Again, like I said, this is very rare. You would, you could, for instance, use the alter table statement to change the schema. So you would say alter table blah, add blah. Basically what that means is I'm altering the table and adding a new attribute. Okay, so in this case, I'm adding a new attribute corresponding to phone whose default value is unlisted. And I can also drop an attribute that I don't want, so I would say alter table bars, drop blah. Okay, so license in this case. Okay, so let's see how much we can cover in the next couple of minutes on converting the ER format into a relational format. So, so the first thing to remember is that the basic cases are actually pretty straightforward. So the way I would transform an entity set into a relation in the relational model is to simply have a relation with the attributes of that entity set. The way I would transform a relationship R into a relation in the relation model is to have a relation with the attributes being the keys of the related entity sets and any attributes of that relation. Okay? So how do these things work? So let's take this example. I have product, company, person like we saw earlier. If I have a product, if I was trying to convert the product entity set into a relation, how would that look? Yep.
Product would be the name of the table, and these two would be the columns.
Yes, so product would be the name of the table. These three attributes would be the attributes or the columns of the table, right? So, okay, here it is. So you have product is the name of the table. I have these three attributes, and then I could add entities within that, right? So that's how I would convert an entity set to a relation. The way I would do this in this particular case would be to use the create table statement with create table statement with product name, and then I would have name type, category type, product price type. I have not written that in this case, and then I would say primary key name comma category. Yeah.
So when you specify the combination of name and category as primary key,
Yeah.
so that means the combination is not repeatable. Is that correct?
Yes.
So for example, say name is A and category A1 and category is B1. So A1, B1, and A2, A1, B2 are allowed.
They are allowed. Yes. Okay. And then let's talk about a relationship. So how do I transform makes into a relation? Any ideas? So let's start with a simple case, right? So one simple case to capture, one simple way to capture makes within a relation would be to take all of the attributes of product and all of the attributes of company and all of the attributes of the relationship, right? So that would be one way to do it, but that's wasteful, right? So it's wasteful because you're repeating the same information in the two corresponding entity set relations, right? So you don't need to record all of that information. All you need to specify the relationship between two entities is to use the keys. So the way I would do that is to say I would capture the key attributes of each entity set, and they would become attributes of the relation, and the attributes of the relationship also become attributes of the relation. Right? So you have these two as key attributes of product, this one as key attribute of the company, and this is an attribute of the relation or of the relationship. So transforming the makes relationship into a relation in the relational model would be something like this. I would have a table called makes with the product name, product category, company name, and the start year. So these 4 attributes. Okay, these are sufficient to signify the relationships between the entity sets or the entities in the entity sets. Yes?
If makes had another attribute, would we also include that in key?
Yes. So if you had, let's say, I don't know, date or end date, let's call it end date, you might have that as a separate attribute. Yep.
What is the key of makes?
So the key of makes, that's a good question. What's a key of makes? So the key of makes is actually the combination of P name, P category, and C name, because that's what is defining the rest of the attributes. Yeah. Between?
The mix has the name stock price.
Huh? Sorry, speak up.
What is P name?
Product name.
Then doesn't it create a dependency between makes and the product?
You have to, so yes, it creates a dependency between the makes relation and the products relation, but you have to specify that information in some way. You can't avoid specifying that information, and that's why you do it in this way.
Is there something like a reference that you can point from product to company? Because creating a make entity create redundancy.
So, okay, so this is in fact this is less redundant than any other mechanism that you can use. So what you're thinking about is a physical implementation, like a pointer or something. That you can't use that because you want the relational model to be decoupled from the underlying implementation. So the only way you can use that is to use these identifiers or the names to specify the relationship between these two relations in the relational model. Okay. We'll cover all of this and take other questions in the next class. Okay, so I'll see you guys on Monday.